Hello, this is Eric from UNC Charlotte. Using mutexes is the simplest way to solve data race conditions. However, improperly using mutexes can lead to deadlocks. We will see today that Kaufman figured out precisely when deadlocks can happen, and this knowledge can be used to design codes that will not deadlock. This is a basic code that uses mutexes to have multiple threads access a common variable. The many threads will have to wait for locking the mutex. This will cause the threads to have to wait for their turn to access the variable. While mutexes are powerful, we need to be aware of situations that will deadlock the application. Consider this code. The two functions f1 and f2 are incrementing a variable as seen previously. But here, each function uses two mutexes. Note that each function takes the mutexes in different orders, so it is possible that the thread that executes f1 takes mut1, while the thread that executes f2 takes mut2. Then we are in a situation where each thread attempts to lock the mutex held by the other thread, so both enter a waiting state, and neither will ever wake up. This is a textbook deadlock situation. The system reached a state where all the threads are waiting on an event that will never occur. Edward Kaufman identified 4 conditions that are necessary and sufficient for deadlocks to occur. If a system deadlocks, then these 4 conditions are true. And if these 4 conditions cannot be true, then a deadlock can occur. The first condition is mutual exclusion. There are resources that are held exclusively by the threads. The second condition is hold and wait. Not only the threads have to hold a resource, they also wait for another one. The resource holding needs to be non-preemptive. Only the thread that holds the resource can release that resource. And finally, there has to be a circular wait pattern where each thread waits on the next, and the last thread waits on the first one. Knowing Kaufman conditions help design systems that cannot have deadlocks by construction. One strategy, for instance, is to always take the locks in the same order. If you have a total order on the locks that you take, then there cannot be a cycle in the threads. This breaks the circular wait condition, and the system is guaranteed not to have deadlocks. Another strategy is to implement a back-off policy. If the thread cannot acquire all the locks it needs, it will release all the locks and try again later. Backing off guarantees that the hold and wait condition is not true. SQL databases typically implement the concept of transactions so that individual connections see the database as if they were the only connection. This forces each transaction to log the table it accesses. One can get in a situation where multiple transactions cannot coexist. In such a case, the transaction manager cancels some of the transactions and reverts the changes that they caused. This ensures that the no preemption condition remains false. If one is locking multiple mutexes at once, C++ provides scoped locks that implements a deadlock avoiding algorithm. This is not fail-proof. Scoped locks can only avoid deadlocks if each thread takes all of its locks at once within a single scoped locks object. Finding bugs and solving them can be tedious in all applications. But in a parallel context, finding bugs can be frustrating because a buggy execution may not be easy to reproduce. Timing bugs, such as deadlocks, can be hard to find. This is why it is usually preferable to design codes that are guaranteed to be correct by design. Kaufman conditions provide us a theoretical framework to find strategies to avoid deadlocks entirely.